In this video, we will explore different ways of controlling a robot in Genesis AI. We will reuse the hello example from the previous tutorials. In this example, we loaded a single plane object and a Franca arm into the scene. We also added a camera for video recording. Here, we move the import numpy to the top of the file. In order to control the robot arm, we first need to map the joint names defined in the mjcf file to the actual degree of freedom index inside the simulator. A Franca arm has 7 revolute joints in the arm and 2 prismatic joints in its gripper. All the joints have 1 DOF only, leading to a 9 DOF articulated body. Having listed the names of all joints, we use getJoint to get a rigid joint object by name. Note that here we are using DOF local to obtain the local index of the DOF with respect to the robot entity itself. When controlling a robotic arm, we want to move its joints to specific positions smoothly and accurately. The controller does this using gains, which are parameters that determine how strongly the robot reacts to position or velocity errors. Usually, these information will be parsed from the imported mjcf file, but it's always recommended to refer to a well-tuned reference value. setDOFSKP sets the positional gain, KP, for the PD controller. The higher the KP, the more aggressively the joint moves toward the target position. The lower the KP, the joint moves more gently, but it might not reach the position accurately. Here, the bigger joints, shoulders, elbows, have high KP, while the gripper, last 2 values, has much lower KP. setDOFSKV sets the velocity gain, KV, for the PD controller. The higher the KV, the robot resists sudden speed changes, reducing oscillations. The lower the KV, the joint moves faster but can wobble or overshoot. The small KV for the gripper ensures it moves smoothly without wobbling, while the higher KV for big joints prevents jerky motion. setDOFS force range sets the minimum and maximum force each joint can apply. If a joint applies too much force, it could damage itself or objects. This ensures the robot operates within safe force limits. The gripper, last 2 values, has wider force limits because gripping objects requires applying more force. Next, instead of using a physical or realistic PD controller, let's first see how we can manually set the configuration of the robot using setDOFS position. We will use a for loop to run the simulation for 150 steps, and we will leave the robot in each position during 50 steps. Note that this hard set of the degrees of freedom can make sudden changes to the robot state without obeying physics. We then call Scene step to run a simulation step forward in time, and camera render to render the RGB images. Rename the video file and stop recording. The model is all set and ready to run the simulation. Run the script. Genesis will be initialized, and the simulation will start. Once the simulation finishes, the camera recording will be available. In this case, we can see that the robot changes state every 50 steps, abruptly switching between predefined positions rather than transitioning smoothly. By setting the DOF positions directly, we are not necessarily respecting realistic physics-based motion. Instead of following natural acceleration and deceleration, the robot simply jumps to the specified positions. Now, we'll switch to a more natural way of controlling the robot using the built-in PD controller. Let's delete the hard set and use the controller counterpart, which respects physical dynamics. From step 0 to 500, we will use position control to move the robot through 3 target positions. The key difference is that, with control DOS position, once we set a target, the controller holds that position. We don't need to send the command repeatedly, unlike with hard setting positions. This makes movement smoother and more natural while allowing the controller to manage forces internally. At step 750, we demonstrate hybrid control. Instead of controlling all joints the same way, we set a velocity command for the first joint, DOF0, while the rest continue following position control. This allows us to mix control strategies, giving more flexibility depending on the task. At step 1000, we switch to force control, setting 0 force for all joints. This means the robot is no longer actively controlled and will fall under gravity. Unlike position or velocity control, force control directly applies torques to the joints, making movement fully physics-driven. At each step, we print two key force values. Get.DOF's control force, which is the force applied by the controller, computed based on the target command and control gains, Kp, Kv. And Get.DOF's force, which is the actual force experienced by the joints, which includes not just the controller's applied force, but also external effects like collisions and gravity. This difference becomes clear when we move from position control to force control. Once the controller stops actively maintaining positions, external forces take over. We again rename the camera video file and run the script. Genesis will be initialized, and the simulation will start. After a few seconds, we can see the progress of the simulation in the interactive viewer, as well the control and internal forces printed on the terminal. Once the simulation finishes and the camera recording is saved, we can open the video. We can see the Franca arm robot smoothly transitioning through different control modes. Initially, it moves to 3 predefined positions using position control, holding each pose before moving to the next. At step 750, the first joint switches to velocity control while the others remain under position control, causing it to rotate continuously while the rest of the arm stays steady. Finally, at step 1000, force control is applied with 0 torque, and the robot collapses under gravity, demonstrating the effect of external forces when active control is removed. By following these steps, you have successfully learned the fundamentals of controlling a robotic arm in Genesis AI. In this first video, we started by applying direct position commands, which override physics, and then moved to using the built-in PD controller for smoother and more realistic motion.